If you look around your kitchen, you're surrounded by complex chemistry that you use every single day. It's in the glass of water you drink, the salt on your table, and the box of baking soda in the pantry. But we rarely talk about these things by their chemical names. Instead, we see this specific shorthand, H₂O, NaCl, and NaHCO₃. At first, these symbols can feel a bit random. Why does water have a small 2 after the H, while salt has no numbers at all? And why does a simple box of baking soda require such a long string of letters? There is actually a highly predictable logic behind these labels. Once you understand how atoms connect, you can begin to write these formulas yourself. This chart groups elements by a property called valency. Think of valency as an atom's matching power. Some atoms have a matching power of 1, others have 2, and some have 3. Knowing an atom's matching power turns chemistry into a visual game. It tells you exactly how many pieces you need to make a stable compound. Let's build a common compound from scratch, aluminum chloride. First, we write the symbol for aluminum, Al, and chlorine, Cl, side by side. Then we look at our table to find their matching powers. Aluminum has a power of 3, and chlorine has a power of 1. To find the formula, we simply swap these numbers. The 3 from aluminum moves to the chlorine, and the 1 from chlorine moves to the aluminum. Since we don't write the number 1 in chemistry, it disappears, leaving us with AlCl₃. Sometimes the atoms have the exact same matching power. Take calcium and oxygen. Our table shows that both of these have a power of 2. If we swap these, we initially get Ca2O2. But in chemistry, if the numbers match, they cancel each other out. They simplify down to 1, giving us the final formula, CaO. This simple result, CaO, is a substance called quicklime. Because it reacts so strongly with water, it serves as the binding ingredient that holds the concrete in our sidewalks and buildings together. We can also tell what is inside a compound just by listening to the end of its name. When a name ends in "ide", like sulphide, it usually means that element is acting alone. It's just a single sulfur atom. But when the name ends in "ate", like sulfate, it means that atom has brought a group of oxygen atoms along with it. They travel together as a single unit. These groups require special care. Let's look at calcium hydroxide. Calcium has a matching power of 2, and the hydroxide group, OH, has a power of 1. If we swap the numbers normally, that 2 lands right next to the hydrogen. Written this way, the formula says we only have 2 hydrogen atoms, but the oxygen is still alone. To show that the 2 applies to the whole group, we have to put brackets around the OH. This acts as a boundary, ensuring that the entire hydroxide unit is doubled, giving us CaOH2. These brackets and suffixes provide a set of instructions, telling us exactly which groups of atoms are working together in a recipe. Now let's go back to that kitchen counter and look at the most complex label from earlier, the baking soda. If you look at the ingredients, you'll see its official name, Sodium Carbonate. We can break this down piece by piece. Sodium and hydrogen both have a matching power of 1. Together, they provide a combined power of 2. Then we have the carbonate. Because it ends in 8, we know it's a group. Our chart shows this group has a matching power of 2. Since the 2 from the first half and the 2 from the second half are equal, they cancel out. The pieces simply slide together to form NaHCO₃. When you look at this label now, you aren't seeing a random string of letters. You're seeing the precise architecture that makes your cakes and breads rise in the oven. Take a look at the products in your own pantry or bathroom. Find a name that looks complicated, find the matching powers, and see if you can swap the numbers to write the formula yourself.